So today I'm going to cover front running, I'm going to cover time manipulation, and then unknown unknowns. And this should allow you to then finish the rest of the CTF levels. And then I think today and next class I'm going to do a lot of in-class time for you to work on these things, because I would say that these are the hairiest levels to solve. So group debugging is something that I would definitely recommend. You're more than welcome to work on the levels with someone else, and then just do your individual screenshots, and that should be good. So the first thing I want to talk about is front running, and this is a special case of a race condition. And so it's a form of a race condition, and you may have seen this if you've taken Charles's security class, 491, 591. This is a classic problem in time of check versus time of use operations. It's also known as transaction ordering dependence. And this is a classic problem in operating systems. You check to see if someone has access to the file, and then when you go and access it, you switch the thing around, switch the permissions around. So that's the classic operating systems problem. Okay, so 15.8% of all smart contracts contain some kind of transaction ordering dependence vulnerability. And the problem with this is that if a miner sees something going in and the miner is participating in a contract, because miners are equal participants, they can mine blocks and they can actually interact with contracts. If the miner has an advantage by inserting a transaction ahead of yours, then this allows the miner to benefit from this. The actual term comes from financial trading. So in case we have any former business majors in this class, this is what stock trading used to look like. This is a picture of the New York Stock Exchange trading floor in the 1930s. And initially, the way you traded stock is that you called your broker, and your broker is sitting here on the trading floor and say, hey, I want to buy 100 shares of IBM. And the trader will go and then try and find someone who's selling 100 shares of IBM, and then they make the market. I have a sell order, I have a buy order, I'm going to make the market, and then I'm going to do the transaction. And so these things are typically carried between traders, person to person, back before computers changed all of this. The floor doesn't look like this anymore. The floor looks like a bunch of computers now, and it's like super small. But this is the way it used to be. And so the front-running sort of vulnerability is that the broker wants to make even more money than the commission that he's making on the actual trade itself. And so if he or she sees a large order of buy IBM going in, he knows that buy order is going to wipe out all of the highest sells, or all the lowest sells, and then the stock price of IBM is going to go up. So what he's going to do is he's going to buy a huge amount of IBM stock ahead of time. Then he's going to submit his client's order, and that's going to even further increase the stock price, and then he can sell all the stock right after that, so that he can make an even bigger profit. So that's front running. And this is outlawed, obviously. So you can get in big trouble as a trader if you're doing this kind of stuff. But we have the blockchain, and there's no laws on the blockchain. So heck, I might as well go ahead and do this because, hey, it's all anonymous and nobody knows any better. Here's one scenario of this happening. I have a prime factoring smart contract. I have an RSA number I want to break very badly. And so, here's N, prime 1 and prime 2. I know the composite public key. And so I want someone to create a solution to this prime factoring problem. And then if someone has properly done this, created prime 1 and prime 2, I'm going to send some money, some cryptocurrency back to the caller. And so say Alice successfully factors the RSA number, submits a solution. the devious miner can see that Alice has submitted prime 1 and prime 2, and then rather than submit her version of submit solution, the miner repackages his own and then just steals prime 1 and prime 2, and then submits the transaction with a higher gas price, so that all the miners, because the miners want to make money, will take the miner's solution over Alice's. And then Alice is left without her rightful solution. Okay. Any questions about that? It's pretty straightforward. Here's another walkthrough scenario. So I have another puzzle solver contract with a balance of 100. I then create this puzzle. I set the puzzle and I create a reward of 100. Anyone who submits a correct solution will get the reward sent to them over here. And then the owner can update the reward anytime. So if I want to, increase or decrease this reward, I have this second function that I can do that for. So the expected operation, if you're trying to faithfully play the game, you believe that this is going to happen. That, okay, I see the game, I need to find a solution, submit it, and then get my reward. And so here is a legitimate user, found a solution to this puzzle over here on the left, submits it to a block, and the block has a bunch of other transactions in it. And then that gets validated. So the miners will mine this block. And because submit solution has been called, you'll hit this thing on the right. And then you'll be sent a reward. And then you'll get your 100. So that is what you expect to have happen in this scenario. So you're happy. This is not my animation. I don't know where I got this from, but I got it from someone else. And then the malicious contract operator scenario is this way. So I just want to get free work from other people. I have this game that looks legitimate. And then when the user solves the puzzle, then what I can do as a miner, I can call update reward on the same block, because this has not been mined yet. I can say update reward to $0 in the same transaction, and then the miners will, because I've boosted this gas price on my update reward transaction, I can then do both of these. And of course, if the gas is higher, you will execute the higher transaction first. So the gas price, you make the gas price higher than what the solution has, and then you update the reward first, and then the submit, and that sets the balance to 0, and then your submit solution sends nothing back to the solver. All right, so that's another scenario of this happening. So the intuition, the observed state is not equal to the execution state. So the innocent victim thinks that the reward is still 100, but when it actually executes, someone has cleared that thing out to 0. And these transactions don't have an atomicity problem. You can't both check and transact at the same time. It's not like a database system where you have an atomic set of commits. They either all go through or they all fail. It's not like that. Okay. So this can be a coincidence, 2 transactions happening at the same time, but it obviously can be malicious. Okay, so here's an actual example. This is a front-running example on the Bancor market maker for ERC20 tokens. So you're buying and selling and trading these tokens, and you have a market maker kind of functionality that's mediated by the smart contract itself. People are putting up sell orders, people are putting up buy orders, and the smart contract is intended to mediate this fairly. And so this person figured out, this is a couple years ago, that you could get a 117% return on investment, and this was a proof of concept, so he basically was the intermediary for a bunch of these, set up a miner, and then for every transaction going through the Bancor contract, he inserted himself as a front-running market maker. And then was able to start making money off of this pretty easily. And then, of course, because this is a white hat hacker, basically showed that it worked. I mean, he could have made a lot more. Showed that it worked, and then sent the money back. Okay. If you click on this, I think it'll give you the link. started making these things clickable so that you can, if you want to visit the article, you can go there. He's actually got a YouTube video of showing you how to do this, showing how he did this, which I think that's actually in the next slide. I put a link to the YouTube. Okay, so how does this attack work? So the buyer submits a transaction to purchase tokens to the network, and it's broadcast immediately to all of the full nodes as a pending transaction. And then it's added to a common queue. This is sort of like the mempool in Bitcoin. There's a common queue of transactions in Ethereum that are meant to be processed next. And so the transaction is not confirmed until you get the block confirmation hash mined. So when you go to Etherscan and you see the thing pending, that's basically because it's in this pool, waiting to be selected by a miner, and then waiting for that miner to successfully mine the block so then it can be confirmed. And until then, all of the ordering of all of the pending transactions in that pool is malleable. You can shift those transactions up and down. So the miners are continually sorting these transactions by gas price. And then any user running a full node can spot a pending transaction going into Bancor and then insert one right before that. You can actually insert the buy and the sell before the subsequent buy by the client. Okay, so if a large buy is about to happen, you know that this Bancor token price will increase. And this is following a deterministic formula in the contract. So you actually know how much money you're going to make by doing this because it's algorithmic. So you put in a buy before that transaction to get an instant appreciation on your tokens that you buy ahead of time. And you're guaranteed that return. If you see a large sell is about to happen, then you know similarly that the token price is going to go down. And so you would basically put in a sell so you can get that higher profit before someone else sells. Okay? And so this is it's basically 6 minutes, and he walks you through how this thing works. Okay, so here's another example. So that was front running. But front running is just a sort of an example of race conditions. And so here's an example of another kind of race condition. And so on the previous one, the race condition is being leveraged by the server, or basically by the miner. In this case, the race condition is being leveraged by a malicious client. So you have a bank contract here that's storing Ether. And then there is this user balances mapping that says what is the balance for this particular user so that you can properly withdraw and transfer money. This contract has a transfer function that moves the balance from one user to another if there's enough funds in the sender. So I can call this, and then I can say, hey, send the balance. Well, I'm going to send this amount, and I want to send this amount to a particular address. And so this thing checks to see if my balance is greater than that amount, and then updates the mapping to indicate that transfer. The other thing that it has is this withdraw balance function. And it says the amount to withdraw is my user balance. And if this holds, let me see, if my balance, withdraw balance, oh, this is withdrawing my entire balance. So what it does is it figures out how much I'm going to withdraw based on my balances. It sends the balance to myself, and then it clears out my my account. So what is the issue with this particular construction? Because it looks reasonable. Yes. This is correct. So you can, it looks like if it's atomic, you would get one function called, then another function called. But if it's not, then you could, if you send multiple transactions simultaneously, we'll do a simpler one. If I simultaneously try and execute transfer and withdraw at the same time, then if they can both be included in the same block, then I might be able to double spend. Okay? Because the actual state change has to be written out in a, like, you're basically updating both of these things in separate transactions, but the actual state that gets changed has to happen in the next transaction block. So that's the issue. So this is a cross-function race condition, and this actually was in the DAO contract. So people were like, oh, it's got this really bad reentrancy bug, but they eventually, after the person wiped out the contract, they also found that there was actually this as well that could have wiped the contract out. So simultaneous execution of both the transfer and the withdrawal can allow you to double spend, or double withdraw, basically, the thing. Okay, so what would you do to avoid this? What kinds of things in computer science would you do? Make a lock, yeah. So here's an example. We saw something similar before when we were talking about the unchecked calls. You do a mutex, a semaphore, a condition variable, or something that will lock out one versus the other. One of the problems with putting these things in smart contracts is the same one that you get in operating systems. You can get deadlock and live lock when you're doing this kind of stuff in operating systems. When you're doing it on smart contracts, you can get that as well, except you can't like reboot a smart contract like you can reboot an operating system, right? Like if you're deadlocked, there goes all your money. So you really have to make sure you've got this right, otherwise your whole contract is blown up. So here's an example where they're trying to add locks around these critical sections where you're trying to change state atomically. So you just have to make sure that your logic here is correct. Okay, the next class of vulnerabilities is time manipulation. This is also known as timestamp dependence. So the time is tracked via this block.timestamp, and this is what gets returned when you use the alias now. It just figures out the last timestamp and then it just returns it. And so this is often used for locking a token sale or locking funds at a particular time. So say you want to like start a contest at midnight, then this might be something that you would use to set the time. The problem with using this is that timestamp is actually determined by a miner. The miner is figuring out what timestamp, the actual value of the timestamp to use. And so there is some leeway for the miner to manipulate this value if it benefits him or her. Okay, so you have to make sure that any contract that you write avoids relying strongly on the actual advertised time. You don't want to rely too heavily on it. Okay? So in particular, don't use it to generate random numbers in your contract, because the miner can figure out what random numbers are going to go in based on the time that he or she mints in the block. So here's an example, a lottery that uses block.timestamp to generate numbers, and the miner either selects this timestamp so he or she can win. If there isn't a suitable timestamp that allows this person to win, then they can select a timestamp so that no one else can win in the current block, and then he or she can repeat the attack on the next block. So that's an example. Here's a code vulnerability example. So here's a game that plays out the very first player at midnight. So if you are the first player, you've never played before, and you're the first player beyond this timestamp, then you can basically get all of this ether, 1,500 ether, that's just a joke, because that's a lot of money. So a malicious miner can include this, his or her attempt to win the game, and then set the timestamp to midnight before midnight. So maybe it's like 11:57 or 11:58, and there is some slush time where even though the timestamp looks just like skewed too early, there is a point, there's a threshold where you can accept the timestamp even though it appears early in these Ethereum full nodes. And so this is what the miner would do. The miner wants to be the exact first person to do this, so sets the timestamp sort of aggressively, and then mines one with a transaction that the miner has put in to win this prize. Okay. The last one I'm going to cover today, and this is the subject for all of your labs, so 3.8 and 3.9 are falling under this one. This is everything else, unknown unknowns. And the reason why I put everything else here because if you had unknown unknowns, this thing would be blank. This is a YouTube clip of Donald Rumsfeld talking about unknown unknowns. If you want to get some humor in your day. So I put everything that doesn't fall under the other 9 in this unknown unknowns. One thing is usage and logic errors. So here's an example of a logic error in a smart contract. If you look at this, it's got a game, and the game can add 2 players, and the contract can take any 2 players, and if 2 players join, they send enough ether, basically 1,000 ether, or wait, 1,000 wei, then basically it allows these 2 players to play. But if you look at this smart contract, if you enter if you call this function and you don't have 1,000 attached to this thing, the smart contract eats your money, right? Like it just takes it from you. The other thing is that the code takes your money if you're not player 1 or player 2. If both of these things did get set and you accidentally called it, then you basically have, you know, the money being, so what you should have done was instead of return 0, maybe I should just do a revert. Say, hey, you can't add yourself because you don't have enough money or you're not one of these players. So this is a logic bug that this particular smart contract has. Another logic error is that you have a smart contract that doesn't penalize bad behavior. So we talked about how hard it is to get truly random numbers on the blockchain. One way to get sort of a random coin flip game to work on a blockchain is to use something called bit commitment. And so if you are trying to do a fair coin flip, one of the things you can do is you can have each player generate a random number and then publish a keyed hash of that random number and then broadcast the keyed hash to everybody on the blockchain. So this doesn't reveal your random number, but what it forces you to do is it forces you to commit because you can't generate that hash with other numbers, right? And so then after the hashes have been broadcast, you can then reveal your random number and then everybody knows that yes, you committed to that. Okay? So the problem here is that someone has to reveal their random number first. And so if you have 2 players, they both broadcast their hashes, and then one of them reveals their random number, the other player immediately knows whether or not he or she is going to win that coin flip. And then what they can do is they can just say, I'm not going to reveal my random number because I'm going to lose. And as a smart contract, you have to penalize that player that refuses to reveal their random number in order for the game to be fair. So that's what you need to do. So you have to, if you're doing this, you have to implement a timeout that penalizes a player that doesn't reveal the random number. Okay? And then you have to verify that that was the intent, that player that didn't reveal the random number wasn't being attacked, wasn't being bombarded with a denial of service attack. And you can't, right? Like, so that's life on the blockchain. Okay. Basically, don't play random games on the blockchain is, I guess, with real money actually is the lesson. Another thing is malicious contracts. So this is an article from last year where people are putting intentional backdoors into contracts because they don't want to be like the DAO. They don't want to have all of their funds locked up in some code that they can't pull out an emergency trapdoor on. But if the good guys can do this, so can the bad guys. So how do you know whether or not that contract, out of its own protection, is doing this, like putting backdoors in there, or the contract is actually malicious? It's saying, hey, I am the new DAO, invest in me, and then I have this thing that prevents the old hack from happening, that can withdraw all the money, you get all this money in, and then you just pull the trap anyway. So that's the real problem, is that what is the intent of the person deploying this contract? And you can never tell. So this is a huge concern. And so this is a quote that I liked over the summer. Blockchain gives us confidence that the smart contracts will operate as coded, But regular users, how are they going to look at that bytecode and see what's been coded, right? So they have some notion of how that contract is going to operate. So they have some intention, well, they have some belief on the intention of that smart contract, but unless you actually look at the code, you have no idea. So that's the problem. So here's an example, which was last month. Somebody tweeted, there's this Fairwind, this is, I think in Asia, I think it was in China, like it blew up in China's social media, that, hey, you know, here's this new game, everyone throw in money, you'll make money. It's like a pyramid scheme, but it wasn't marketed as a pyramid scheme, and this thing took off. This is sort of like multi-level marketing kind of stuff that was happening. And then somebody, and this was over the period of a month, this thing took off. And people were monitoring Ethereum, and they're like, wow, this is like taking up 40% of all Ether in all the transactions in the block. So this is like a huge percentage of what was running in Ethereum in September. And then somebody realized, hey, there's some like vulnerabilities in here that allow the owner to totally drain the balance, that allows the owner to prevent other users from withdrawing their balance, and then that allows anyone to basically steal new deposits. And this was reported on the 27th of September. And then someone else tweeted, this could probably be one of the biggest scams ever in Ethereum, because they looked at this code and it was like, hey, this is basically a Ponzi scheme being run, because, you know, it wasn't marketed that way. But then eventually people were looking at the code and they're like, okay, who is contributing the money that people are then pulling out of money? And it's basically new deposits are driving the profit of the old accounts on that. And so within a day of this happening, you can see it went from nothing to like basically 10, how much was this? 10 million? It was 0 to 10 million in about a month. And then within 2 days of this being reported, it was all gone. And they don't know where it goes. I mean, there's some addresses that they know this went to, but yeah, now it's empty. And you can click on, that's the contract address. And I think this is clickable if you're interested in reading more. Here's another one. It's called Oyster Token. So when they say it's like an S coin, this is the kind of stuff that they mean. So this is Oyster Token. It's an ICO. And typically when you have an ICO, you're raising money in one shot. You have one sort of fundraising round, and then you don't want it to be possible for that smart contract owner to issue another round to dilute your original investment. So typically in real life, you wouldn't do this. But in a smart contract, you can code this in there. And someone realized that there was this only director. There were these two functions that were protected by only director, and this is basically the contract deployer, that basically allowed you to reopen the token sale. So this closes the sale. So only the director can close it, but it also has this open sale where you can reopen the token sale. Here's a similar one, a funfair token. You have this controller, this only controller thing, that allows you to wipe out any balance of the contract and allows you to do any kinds of transfers if you are the controller. Now, you don't really want to do this. So this is basically God mode in this smart contract, which is what the blockchain was intending to get rid of, right? So now, whoever this controller is can basically manipulate all the balances in that smart contract. And so even though you could have been derived from ERC20, if you are implementing these kinds of things, you can basically override the balances and then not have it be above board. Okay, another class is incorrect assumptions. And this is the one, so these are the things that you're going to be doing for the next two labs. There are some assumptions that contract authors often make that are not true. The first one is that no one knows their address until they're actually created. So when you are about to create a contract, you have this assumption that, oh, that contract address is going to be random. No one's going to know it ahead of time. That's not true. There's also an assumption that these addresses, when you create them, will have no balance initially. that there's no ether associated with a newly minted contract address. This is not true. And then another assumption is that they can only be sent ether via payable functions, including the fallback function. That there's a limited number of ways to actually accept currency into your smart contract. Okay, so these are all not true. The contract addresses that are created are predictable, and it's predicted based on the creator's wallet address, and the wallet address is nonce. The contract addresses, if you know them, can be sent ether ahead of time before they're even created. And then finally, you can be sent ETH in a self-destruct of a contract, which we've already done. That was actually our first smart contract, is showing you how to do that. Okay. So this is an example of how that assumption breaks down. There's this gridlock bug in the lock drop contract. And this was fortunate. This came out in the summer. I didn't have an example of this. But then basically the CTF levels and this thing came out. And so now we have an actual example of this causing an issue. So this is a smart contract bug that, this is a smart contract that had basically $900 million worth of ETH locked up. And it had this bug where it had assumed that a contract address would not have any balance associated with it before creation. And we'll look at the code right after this. And so the idea of this smart contract is that if you have some investing operation and then you want to be able to take money from your investors on the left into this lock drop contract and then lock up those funds in separate smart contracts for a short duration while you actually do something like, it's sort of like a bank, like a certificate of deposit in the bank. You say, I want this thing to be there for a year, and then after a year you'll release it. That's basically what the lock drop contract is doing. Okay. So here is the code for doing the lock. It basically looks up the ETH in message.sender. So it's basically getting the amount of ether being sent. It's getting the owner of it. And then based on a term of, sort of a lock time term, it's basically creating a new lock contract with that amount of money. And then it's basically creating it with this owner address and an unlock time. And then what it does right after it is that it asserts that this balance is equal to the message value. Okay? So what happens here is that if someone has figured out what this address is going to be deployed at and adds some ether to that address ahead of time, then this is not going to be equal to message value, right? Because if you send one ether and then someone pre-sends one way to this address, then this will always fail. And then you've really locked up the entire contract, because then this thing can't work. So that assert assumes that the contract didn't receive any other ETH, either before or after the creation. And so what you would need is this, where the balance has to be checked to be greater than or equal to the message value. Okay, any questions about that particular code? That's really tricky, actually, to think about. Okay, and that's the vulnerability in red. Okay, so the remediation for this is to don't over-assert, remove any of the non-obvious behavior from the programming language in the virtual machine if you, or understand it before you use it, and then always assume that the smart contract has bugs. Yeah?
I was wondering about that assert on the previous page.
Uh-huh.
What is the purpose of doing that assert after you create the new contract?
Just to make sure that the new contract was correctly created.
Okay.
Yeah, and that is the whole thing. I mean, that's one easy check to make sure that the lock contract was created successfully. Yeah.
Okay. I was just wondering if there was like a different check for contract creation that you could do that would be less prone to lockup.
Good question. I don't know, actually. Yeah, that actually checks all of it, including whether or not there was enough money or it's the exact money that got sent. Yeah. Okay. So with that, that's all I have in terms of the lecture. Now I'm going to actually go through a walkthrough of these levels, because these levels are the hardest ones in the CTF. So I am going to walk through slot machine, rainy day fund, and scratch card. And these are the levels that you'll be doing this week. So the first one is slot machine. So here is the victim contract. This one's pretty trivial, actually. This is probably the easiest one outside of donation. The other two are hard. So this is the victim contract, and you see that the winner, the amount that you need to win is 5 ether, and it's basically got a fallback function, and it requires that you the amount that you send the fallback has to be equal to 1 zabo, which is like a dinky amount. And then if you are able to contribute a zabo, and that zabo gets the balance of this thing, of this smart contract, to be bigger than 5 ether, then you get the whole thing. That's it. That's the whole smart contract. Okay? And it starts out with like 3.5 ether. So you need 1.5 ether to be added using this fallback function in order to actually get the jackpot. So if you're sending this thing 1 zabo at a time, you're going to be there forever. I don't think incompletes will last that long for you to do that. Moreover, the time to do all of these transactions and the gas required to send 1 zabo at a time, programmatically even, to the smart contract is infeasible. I mean, you're talking about at least 1 million. I think a zabo is, I forget, 10 to the minus 6 ETH. So are there other ways for a contract to gain ETH? And you've already seen this. There's 3 ways. There's the self-destruct call, which we've done before. You can send the ETH to the contract before its creation. So before you create the level contract, you can actually precede it with that 1.5 of ether, so that when it gets created, it adds up to 5. So that's another way. And if you want to solve this level this way, that's the truly elite way of solving this level. But the easiest thing to do is to just self-destruct something into the contract balances. And then the last one is to mine a block. If you want to run a miner, actually this is the truly elite way of solving this. Run a miner, and then you set the reward to that contract's address, the reward address. So typically the miner will specify his or her address as the reward, like the block reward should go to that address. But if you want to win this pot, you could set it to the slot machine address, and then the rewards will go to that contract address rather than yourself. So those are the 3 ways. So for this way, I think he is intending for you to do the self-destruct way. I'm pretty sure. Okay. Use one of the above methods to get the ETH to 5, and then send the contract 1 zabo, and then receive the balance is that one. So include screenshots as before, and then this is a very simple contract, but we still want you to put this into your your GitLab, in your repo. That's what I'm going to do. Okay, so the next one is rainy day fund. This may require a lot of ETH for you to debug and solve. So pre-retrieve, maybe, well, if you're really good at following directions, it should only take you about 3 ether, 3 or 4, however much for a contract deployment. But if you make a bunch of mistakes, like I make a bunch of mistakes, this thing took me a lot of ether to solve. So don't feel bad if you're like continually bricking your contract and then, you know, having to go to the faucet over and over again, because that was basically me. So you need at least to burn the initial 2.5. Well, you might need to burn the initial 2.5. Actually, I think I have it set up so that you won't, but okay. So I cannot stress enough that you go through this walkthrough very carefully to keep from losing your ETH, because all of the work that you need to do happens before you even say deploy the level. So hopefully none of you have deployed the level. Otherwise, that 2.5 ether that you used to deploy the level, that's already gone. So that's what I want to cover on this one. This particular level exposes the fact that contract addresses are predictable. And so they're derived using two values: the wallet address of the creator. So the creator of the contract has a wallet address. It's based on that address and the creator's nonce. So when you have a wallet, every transaction you submit to the blockchain increases your nonce by 1. So your nonce starts at 1, and then for every transaction that you submit, it increases that nonce by 1. So if you look at your MetaMask and you see your transactions in MetaMask, they're incrementally increasing. That's your nonce, basically, that MetaMask is reporting. Okay. So contract addresses are a simple deterministic function of both of these two values. There is a script. I think it's in your repository. This is, or no, it's not. It's actually, you can just copy and paste it if it's not in your repository. There is this simple script. Given a sender address and the sender's nonce, will generate the very next address that wallet will create based on this current nonce. Okay, and this script requires in Python this ether utilities package and this RLP package. The RLP package is this recursive length prefix encoding package. It basically serializes all of the Ethereum stuff into a particular. All of the Ethereum objects are serialized into a byte, a payload of bytes. And so the address of the contract is, and you can just use this as a black box, but basically what's happening is it's taking these bytes for the sender address, it's generating these sender bytes, and it's RLP encoding the sender address along with the nonce that the sender currently has, and then it takes a hash, a KK hash of this, and then the address is pulled from the hash deterministically, and then that's effectively the contract address that it's going to create with that particular nonce. So in this case, I have a loop here at the bottom that says for nonces 87 through 90 of my wallet, this is my wallet address. So for that, I'm going to print for the particular nonce x, which is my loop condition, or my loop variable, print out what this thing returns, the MK contract address. And this will be the contract on the blockchain that gets created with this particular nonce. Is that clear? Okay. So this is how you run it. You set up a virtual environment, you activate it, and then you install those packages to get the Ethereum utilities, and then you run it. And so if I run that thing straight up, it gives me these addresses for these nonces. And after you do this for your own wallet address, and then go back into Etherscan to make sure that you've properly generated the addresses for your wallet. And I'm going to show you how I properly generated it for mine. This is what the script emits. And then I go into Etherscan and I look up my wallet address. And back when my nonces were back when my nonces were 87 through 89, it was basically, about 131 days ago. And these are these three contracts that were created. And so if you click on one of these transaction hashes, so this is contract creation, I click on this, it gives me this hash. If you look down, here's my wallet address. This is the contract address that got created, and this is the nonce that created it from my wallet. So my nonce 88 created that contract address, And if you go back and you look at the output of mk.py, so address, nonce, if you look at mk.py, it says for nonce 88, you get this C4B5371, and that's the actual address that gets created. So that's the first thing you should do. Make sure you can get mk.py to properly predict the addresses that your wallet is creating on the blockchain. Okay? You can then click on the next one. So if I click on 75C7, and you can see this is nonce 89. I see 89 with my wallet address, gives me this 33E9, and I go through the script output, and 33E9 is the next one. Okay, so that's the first thing to do. And then this is the level. So the level has two contracts. There is this debug authorizer contract, and it's got a single Boolean, and this Boolean says whether or not to put something in debug mode. And if this contract is instantiated with 1.337 Ether, then you set debug mode to true. And the idea here is that the developer of this smart contract is going to set this to 1.337 if he or she needs to figure out to debug the thing. So that's the model. So they want to debug this rainy day fund contract, which is below. And the first thing that this rainy day fund contract does is in the constructor, it creates this new debug authorizer. Now, initially in debug mode, you would have this line instead of this line. And so you can see that it's commented out. Like any good programmer, it sticks the debug code in there and then comments the thing out in production for everybody to see. And so they're allowing us to see that this typically would enable debug mode. And if you look, the debug mode, if you have this thing, debug authorized debug mode, if that thing is true, then it's basically acting as if you're a manager of the contract. It basically disables all the protections in this smart contract. Okay, so in the constructor, you create the debug authorizer, you set the developer to the whoever is the contract creator, and in this case it's the launcher contract. And then you set that the funding manager is functionality is enabled for the creator of this contract, and then that is the only address that is allowed to be a manager. So this prevents you from being a manager on this half. And so your goal is to enable debug authorizer mode on the level ahead of time is the exploit. And then there's a simple withdraw function that says if you're a manager, just transfer this thing over. Okay? Is everyone clear on what this contract is doing? This is it. This is pretty much the whole contract. And so the exploit is to see, before this debug authorizer contract is instantiated, to see if you can put in 1.337 Ether at that address ahead of time. And then when your level gets deployed, it'll automatically get deployed with this debug mode turned on. Okay, so now I'm going to walk through how you do that, because it's actually quite complex. So the first thing to do is examine the contract that has created your rainy day fund contract. And of course, if you haven't deployed it yet, you have to figure that out. And I would figure that out by just reading the slides. So you don't have to deploy a contract and look at this. I'll give you the address. So the wallet, when you initiate, this is how the level contract gets instantiated. You send money to the overall game contract. So this is the address of the SICTF, the overall contract. And then this wallet this smart contract will basically call and transfer the money over to your rainy day fund launcher contract. So this launcher contract is what's shared across all of us. When any of us deploys a rainy day fund contract, it'll be done through this address. So this is the thing that creates all of it. And then this rainy day fund launcher contract will then create our our own individual contracts in this CTF. And moreover, so the launcher creates the level, and then the level, the first thing the level does is create this debug authorizer contract. Okay? Now all of these addresses, the level contract address and the debug authorizer contract, those are all deterministic. So the whole point of this level is to figure out what this address is and to figure out this address ahead of time. Is to predict those two addresses ahead of time and then send the ether 1.337 ETH to this one. Okay. And so we're going to use mk.pi, and then the address is found, and you would start from the game contract address. The game contract address has this plus a nonce. So you need to figure out what its current nonce is. And if you know what its current nonce is and its address, then you can get the launcher address, and then, or you can get the level contract address and the debug authorizer one that the level creates. Okay, so on Etherscan, you can click to find the rainy day CTF level launcher. So you copy and paste this into there. So this is the output of Etherscan for this contract. And if you go into internal transactions for this contract, you can see that all the thing is doing is creating a bunch of contracts. So this is from not too long ago, and you can see all the different contracts that have been created. So it seems like this had gone 5 days in between people instantiating a contract. And then what you want to do is you want to click on the last transaction, because the last transaction shows you the current nonce, or you can get the current nonce of this particular contract by clicking this transaction hash, which is what we'll do. If you go to state changes, so if you look at this, there's the internal transactions, and then if you click on this transaction hash, you can go and you can click on the state changes from that transaction hash. And then if you look at the state changes, the state of this particular contract, so this is the launcher contract, went from 161 to 162. So now you know that the nonce for the next rainy day level fund will get created with 162. And then you can predict it. So now I have the launcher address. The launcher address is here. The nonce is here. Now I know what the next rainy day level fund for the next person is going to be. Okay. And then you can go into the internal transactions to reveal the contract addresses that were created in the last level deployment. So we're going to just investigate. We're going to investigate this contract creation, because now we have to predict what the debug authorizer contract is. So this process allowed us to get the level address, but now we need to figure out the debug authorizer contract. And so if you look into the internal transactions of that contract, you can see that you are getting, so in this particular case, my contract, where is my contract address? Oh, I don't show it here. You can see that the contract that gets created has this address, 17902AF. And then if you go into the internal transactions, this particular transaction also creates a debug authorizer contract, F24227B0. So that's basically, so you see that the 2.5 ether goes to the level contract. The level contract then sends that to the launch. Sorry, let me back up. This is the launcher. So the game contract sends it to the launcher address. The launcher address creates the level contract address. And then the level contract address is going to create the debug authorizer address. So that's what this thing is showing you for that last contract creation. And so what you want to do is you want to be able to predict, to generate this address and this address using mk.pi. So that's what I want to show you next. Okay, so the CTF level, if you saw those initial transactions, is doing this. And so you want to validate all of these contract addresses ahead of time. So here's what I'm going to do. This is the launcher. and I'm going to run mk.py on the launcher address and then the nonce 161, and that's going to generate the address that I see in Etherscan. And then this address is going to immediately create this debug authorizer, and because this is the very first transaction that this contract does, then you're going to use a nonce of 1 with the level contract address in order to generate the debug authorizer contract address. And once you have this, you send 1.337 to this address, and then you deploy the contract, and then you win, which is what I'm going to hopefully show you next. So then, to actually solve the level, you are going to do mk.py on nonce 162, because that's the next one that gets created. You get that this is the predicted rainy day level fund, and then from there, you figure out what the nonce of 1 is going to generate as an address, and then this is the debug authorizer address that you would then send 1.337 to. Okay? And so in this case, well, the screenshots for the subsequent, so now this is a walkthrough of the exploit. So the screenshots show how this is done with a nonce 59. The script shows that this is the address that gets created, the level address. This is the debug authorizer contract address. And then the next nonce 60 has those two as addresses. And so you want to, once you get this as being the next debug authorizer that gets created, you just send that thing 1.337 ETH and then play the game. So you either reset the challenge contract, or if you haven't deployed yet, you click play game and then deploy it. And then you win. Okay. Once you do the deployment, you'll get this address. Make sure that this is what you had predicted. And then if that's what you had predicted, bring it up into MyCrypto, and to make sure that the debug authorizer is set to what the address is that you predicted. And then from there, go and see that the debug mode has been enabled, is set to true. And that's when you know your exploit has taken hold. Okay. And then call withdraw, and then get all your money. Okay, and then this is the screenshot I want you to make to get the money out. Okay. So that was a lot. Are there any questions about what you're doing? So hopefully this is like the hardest one, I think, yeah. Yes, so you could be solving the level for someone else. If someone, so somebody could be sitting there hitting withdraw on these, you can generate the list of all CTF, I don't know if anyone has done this. You could programmatically solve this for everybody. You could totally wipe that level off of security innovations. You just generate a list of 1,000 debug authorizers, the next 1,000 debug authorizers, send every single one of them 1.337 ETH, and then win, or you could disable it by sending it, please don't though. Yeah. Well, yeah, and then Mick might actually shut the CTF down, and that would make me very sad, because then I had built all this stuff for nothing. But yeah, you could, that's really that's adversarial thinking. That's the whole point of part of this. So some of the details of this won't matter that much, but your ability to train an adversarial mindset is basically what we're looking for here. Because these things have been built with certain assumptions, and if you programmatically assume those things, then you're lost, you're broken. Okay. Okay, the next one I want to talk about is scratch card, and I saw that someone was already trying to solve this particular one. Hopefully, after I go through this level will be easier. And again, I'm going to give you a lot of time next class for you to actually collaborate to try and get this stuff to work. I definitely want everybody to solve every one of these levels, so I'm going to try and give you as much support as possible, because these are the gnarliest ones. This particular one, so you saw with the heads or tails, that if you are sitting there writing a program to attack that contract, you have all of the variables that that contract has, and then you can programmatically win the coin flip every single time. So scratch card is attempting to make it so that no smart contract can participate. It's trying to make sure that only wallets interact with this smart contract. And the way it's doing this is with this library call to this address, and it's got this modifier called isContract. Oh, it's not a modifier. It's got a function that determines whether or not a particular address has code associated with it. So if an address has code associated with it, then it's a smart contract. Otherwise, it's a wallet. If your extended code size is 0, well, then you're a regular wallet. And so this thing is saying, okay, wallet or not wallet, and it's basically doing this as an embedded EVM call. So what happens is that you have a full copy of the blockchain. You have all of the smart contracts that have been deployed sitting there in the full node. There is a low-level Ethereum and EVM bytecode instruction that allows you to go into the blockchain and figure out if there's code attached to a particular address, because it obviously has to be there in the full node if you're gonna run a contract. And so this particular call just checks what's the size of the code attached to this. Okay, so then scratch card basically is protected by this modifier that says not contract, and it checks to make sure that message.sender isn't a contract. It doesn't have this code size attached to it. Okay, so that's a pretty simple modifier. And then it uses that modifier to protect the play function. So in order to play the scratch card game, you have to be not a contract. And the way this works is that it's going to take some block timestamp, and then it's going to take the modulus, the mod of that times 10 to the 8th, so that it gives you a random spray between 0 and 10 to the 8th minus 1. It gives you that random number, so it's pretty unlikely that you'll win this thing once, let alone 25 times. So this thing wants you to win this scratch card 25 times before it gives you a jackpot. And it's making sure that you can't call it with a program. Okay, so this is making it hard, right? So if you have managed to send a particular amount of ether or way that gets you this, then you win the scratch card. And then you get your money back. So the scratch card value gets returned to you. So you get your money back. And then this counter, if you are a mega jackpot winner, if your win count is more than 25, then you can get this check if mega jackpot winner is called from collect the mega jackpot. So if you are a winner that you've won 25 times or more, I am going to give you 2 times the cost minus the amount that you're withdrawing. Or I'm going to give you two times the cost of your ticket back. So you're going to get double your money back is effectively it. So you're not going to. So this require is limiting the amount that you're getting paid out. Okay. And then finally, I'm going to set your win count to 0 and then transfer that amount over to you. So first of all, does anyone see any obvious errors in this collect mega jackpot or in the play function? Like what, if you were being devious, what would be things that you might think of to try and attack this particular contract? So the labeling here is significant. Like if I labeled scratch card with how many? D10, D3, and D6. Does anyone see where D3 or D6 show up here? What was D3? Anyone remember what that was? Yeah, where's that? Anyone see it? Just to train your analysis. Mm-hmm. That is true, actually, yep. But you would have to do a lot to overflow that. Is there anything else? Yeah, it's the cost minus, does this actually do anything? What is the type for cost? Sorry, it's not all on one page. That's why. So the type of cost is a uint 256. And then the type for amount is also a uint 256. Is this ever false? Yeah, it's never false. It would, yeah, so it's only false when they're equal to each other, right? Because when they are equal to each other, 0 is greater than 0. But that's the only time, right? So I could say, give me the entire balance, and even though the entire balance is more than 2 times the cost, I can still withdraw that. So that's D3. Okay. So actually, this is what these are questions I wanted you to answer. Okay, so then that was the first one. When might you know how large your contract code is?
I think it would have to be when it's running that part. So you could start with it being 0 and then suddenly create a contract at that address. So it's sending a signal that there's 0 code, and then the code gets filled in after the detection.
Uh-huh. You had...
I was going to say, you know how large your code is once you compile it, but you don't have to have it in.
Yeah, when after you deploy it do they know how you're like... So when you if you recall, when you deploy a smart contract, you have a constructor, and a full node will execute your constructor and then take all the bytes that you have sent it. Well, it takes all the bytes and then eventually runs your constructor code and then commits that whole thing into one transaction on the blockchain. And it's only after that whole thing has been committed to the blockchain that that value, this X code size value, is going to be non-zero. Okay? So the issue here is that when you are executing the constructor, that code size is actually still 0. Because you haven't actually committed the contract into the blockchain yet, but you are sitting there executing code, and you can play the scratch card game in the constructor of a contract. And that is the low-level assumption. That's the low-level thing that all of this stuff is abstracting away, that you then are making an assumption that this thing is actually going to do what's intended when it doesn't. And this is how all security problems show up, where you're just got a mismatched set of assumptions. Okay, so the last thing is if you are going to launch an attack from a constructor for a contract that you create, you're going to have to add the attacking contract's address to the authorized senders, right? Because every level has an authorized senders list, and the contract that you're creating has to be added to it ahead of time, because it's sitting there in the constructor trying to execute things. So then you have to predict your contract's address so that it can be enabled onto your level before deployment. So that's that's basically what you have to do. So some preliminaries: you have to find your current wallet, your current nonce in your wallet. So again, this is my wallet address. I click on the last transaction hash that has been recorded, and if you look at when I click on that transaction, you can see that my nonce is 268. So then I know that 269 is going to be the next transaction, and then followed by 270. You can also go to MetaMask, and if you click on MetaMask, here is a picture of your nonce over here. But this assumes that all of your transactions are going through MetaMask. If you have managed to submit a transaction from elsewhere, then of course this won't be your current nonce. So the best thing to do is to always go to Etherscan, because Etherscan has the definitive state of your wallet address. Okay, and so we're gonna need to, we're gonna consume both nonce 269 and 270. Nonce 269 is for me to add my attacking contract's address to the authorized sender of my contract. And so then what I need to do is, after I add myself to the authorized senders with this transaction, I'm going to then deploy my attacking contract on nonce 270. So with mk.py, with my wallet address, and this is a version of the script that takes these things as arguments, I'm going to get the address predicted for 269 and the address predicted for 270. This is the address of my attacking contract. I'm going to go back to my CTF level and then add this attacking contract address to the authorized senders. And this, submitting this, will consume 269. And then what I can do is back in Remix, I can then deploy my attacking contract and then win. Okay. This first nonce, this actually isn't going to be a contract. I have to interact with my level contract in order, in order to authorize the sender. And then that would be 269. It's going to consume that nonce, and then the actual contract gets created on 270 in this particular walkthrough. Okay. So then what I'm going to do is I'm going to create the attacking contract. I am going to make an interface to scratch card so I can play it, and I can, I actually don't need check, but I need the play and the collect mega jackpot for sure to interact with scratch card. And then this is the attacking contract. I have instantiated with that interface, and this is the actual level address that has been created for me that I'm trying to attack. And then here is a variable. I have to win this thing 25 times in a row. And this is all done in the constructor. So the entire attack has to happen in the constructor. And then I create the value that's going to win me this scratch card. And then that's basically deterministic, pulled straight out of the scratch card code. And then I'm going to do this in a loop 25 times. I am going to play with this particular value. And then at the very end, I'm going to call collect mega jackpot because I've won it 25 times. And I'm going to just withdraw the entire balance because that arithmetic check fails. Okay? And then I have this call collect to basically give myself all the ether back. Okay. So when I deploy this, I have to make sure when I do the deploy that I set the value to at least 1 ether. And the reason is because this thing needs at least a sufficient amount to play what the maximum amount of what this gives you. So that's, it has to be able to fund this play appropriately. Okay? So that's what I need to do. And what I also need to do is I need to make sure I have a huge gas limit, right? Because I'm running a loop. I'm running a loop in my constructor. Hopefully, Remix has estimated the amount of gas I need to run 25 times. But you just need to make sure that thing is cranked up. And then when you deploy that contract, you can immediately go into Etherscan, and you should see this. The contract has been created, and then a whole bunch of transfers have happened in the contract creation from the constructor. And the last one, if you go on Etherscan, I'm going to have you go into the internal transactions of that deployment hash. And then at the very last call, you should see that the collect mega jackpot call in your constructor transfers the last 3.5 ether back to your contract. And then you can call self-destruct to get all of it back, 4.5 ether. Okay, so with that, I'm going to let you just get started solving these CTF levels. Are there any questions? All right.